1856, the British physicist Kelvin discovered that the gravitational force of the cable affected its resistance while laying the transatlantic submarine cable. This is the resistance effect of the strain phenomenon in metal materials, which is mainly caused by the change in resistance due to the change in the conductor's geometric shape. In this lesson, we will learn about the working process of the strain gauge of the resistance strain gauge temperature sensor and its practical application. The sensitivity of the resistance strain gauge is strain. When a metal is subjected to tensile forces, it elongates lengthwise while contracting radially. The ratio of the elongation of the metal to its original length is known as strain. A device made based on the principle that the strain of a metal is proportional to the change in its resistance is called the metal strain gauge. The physical phenomenon where the resistance of a metal conductor or semiconductor changes due to mechanical deformation caused by an external force is known as the strain effect. The strain effect is a physical phenomenon. It occurs due to the alteration in the path of electron movement when a conductor or semiconductor material undergoes strain, which subsequently impacts the magnitude of the resistance. This effect is widely applicable in practice. The sensitivity coefficient of a semiconductor strain gauge is several tens of times larger than that of a metal material. Moreover, depending on the choice of material or the degree of doping, the sensitivity coefficient of a semiconductor strain gauge can be positive or negative, meaning the resistance of the strain gauge can either increase or decrease upon stretching. Next, we will learn about the working process of a strain gauge. In use, a strain gauge is typically affixed firmly to the surface of the test object using an adhesive. As the test object deforms under stress, the sensitive grid of the strain gauge undergoes a similar deformation, causing its resistance to change. This change in resistance is then measured by subsequent testing circuits and converted into a change in voltage or current. The detection circuit is used to detect the output signal of the strain gauge. Since the range of resistance change in metal strain gauges is very small, it would be quite difficult and inaccurate to measure the change in resistance directly with an ohmmeter, so bridge detection is commonly used. In this circuit, R3 represents the effective strain gauge resistor affixed to the test object, while R4 is a dummy strain gauge resistor, essentially a bridge balance resistor. When R is unstressed, the bridge is adjusted to a balanced state so that the output voltage U equals 0. When R3 changes due to deformation under stress, the bridge will become unbalanced, resulting in an output signal voltage U0, whose magnitude reflects the magnitude of the force applied. In practical use, besides strain, temperature changes can also alter the resistance of the strain gauge. Finally, let's learn about the applications of resistance strain gauge sensors. The first application is strain force and load sensors. The greatest utility of resistance strain sensors lies in the fields of weighing and force measurement. These force sensors consist of strain gauges, elastic elements, measuring circuits, etc. Depending on the structure of the elastic element, column, tubular, ring, beam, spoke, etc., and the load nature, tension, compression, bending, shear, etc., they can be categorized into many types. Common strain force and load sensors include column types, cantilever beam types, and ring types. For column-type sensors, strain gauges are symmetrically bonded to the middle part of the outer wall of the elastic body where stress is evenly distributed. When connecting the bridge, considerations are made to reduce the effects of load eccentricity and bending moments. Column-type sensors have a simple and compact structure and can withstand large loads. Common beam type sensors include constant section beam type strain gauge sensors, constant strength beam type strain gauge sensors, and some special beam type sensors. Beam type sensors have a relatively simple structure and are generally used for measuring loads below 500 kilograms. Compared to column type sensors, they have greater variation in stress distribution, both positive and negative. Beam type sensors can also be made into electronic weighing scales and the like. The second application is the rolling mill. During the operation of a rolling mill, the rolling force is an important factor. It relates to production efficiency, product quality, production costs, and the service life of the rolling mill, so measuring it is particularly crucial. Resistance strain sensors are most widely used for measuring roll force at home and abroad. There are also other types such as piezo-magnetic and capacitive force sensors. Currently, all major domestic steel mills use disc-type force sensors to measure the roll force, allowing for accurate and reliable measurement of the roll force in rolling mills. The focus of this lesson is on the structure and classification of strain gauges. You can look for instruments that use resistance strain sensors in everyday life after class. That's all for this lesson. See you.